A chemical equation is a narrative description of a chemical reaction. So we start by indicating our reactants. Our reactants are always going to be on the left side of our arrow. Then we have our products. Now, a lot of times when you see a chemical equation written out, you will also see little letters in parentheses. Those little letters indicate the phase of matter. So again, over here on the left, we have our reactants. And on the right, we have our products. So if we were to read this reaction, we would say gaseous methane reacts with 2 moles of gaseous oxygen to form 1 mole of gaseous carbon dioxide and 2 moles of gaseous water. Now, it's possible if you were given a problem in narrative form that you wouldn't be given the numbers, and you would be told that you need to balance the equation. When you're told to balance an equation, what you're looking for are the coefficients that go in front of the chemicals, the chemical formulas, in order to obey the law of conservation of matter. If we have 4 hydrogen atoms on the reactant side, as we do here, we need to have 4 hydrogen atoms on the product side. Now, just with water, we showed 2. So we put the 2 as a coefficient in front of water in order to double that so that we have 4. Now, this timekeeping helps us to obey the law of conservation of matter. So let's say we have water, and I'm going to leave the phase off for now. And water will react to form hydrogen and oxygen. Now, these are all gaseous, but I'm just going to leave it like this. Now, it's also possible that you may see a couple of special circumstances, like a little triangle. This is actually a delta sign. This means there's heat added. So here we have water with heat could form hydrogen and oxygen gas. Now, this is actually a very special circumstance because we know if we just heat water, we're just making steam. So this is a special circumstance under pressure as well, but we won't get into that here. So let's focus on balancing this equation. We have hydrogen and we have oxygen in this equation. I'm going to put an R for reactant and I'm going to put a P for product. On the reactant side, I have 2 hydrogen atoms. And on the product side, I have 2 hydrogen atoms. So at first, it looks balanced. There's only 1 oxygen atom, and I know that because we don't have a number in the superscript. Remember, when we're looking at our chemical formula, the absence of a number is not 0. It is 1. The 1 is implied. But we have 2 atoms of oxygen on the product side. That is not balanced. So we must need to put a coefficient in front of our water. Now, you cannot add anything to the chemical formula because that actually changes the chemical. Remember from a previous video, this is water, this is hydrogen peroxide. Changing that subscript changes the compound. One is necessary for life, the other one will kill you if you drink it. So it's very important that we don't change the compound. We only add digits or coefficients in front to say how many different moles we have. So if I put a 2 here, what that indicates is I have 2 moles of water. And those 2 moles of water are now going to break apart. And I'm going to, let's redo our record keeping here. Let's change our color. So now I have 4 hydrogen and I have 2 oxygen. My oxygen is balanced, but now my hydrogen is not. So I need to add another coefficient, this time in front of the hydrogen. And then that will balance my hydrogen as well. So now my hydrogen and my oxygen are balanced. I have obeyed the law of conservation of matter. And I have shown then with the law of conservation of matter, the decomposition of water, gaseous water, into gaseous hydrogen and gaseous oxygen. So this is what's called a decomposition reaction. You start with one reactant and break it into pieces. Now I could also have a reaction like this. So I start with my nitrogen and oxygen, and that's going to react to form N2O5. Now that's also a gas. First, let's balance this. So I have N and I have O. I have my reactant side and I have my product side. On the reactant side, I have 2 nitrogen, and I can tell that from the subscript on my compound. I also have 2 oxygen. On the product side, however, I have 2 nitrogen, but I have 5 oxygen. Now you could look at this, if you're comfortable with math, you could look at this as the least common factor. And once you find the least common factor, then finding the coefficients is fairly easy. If you're not comfortable with math, you may have to stab in the dark a little bit until you come across something that works. Now because I have a 2 here on the reactant side and I have an odd number over here on the product side, I'm actually going to transfer them. So I'm going to put a 5 here, and I'm going to put a 2 here, and I'm going to see how that works. Let me just give a little highlight there just to make sure that we're keeping things separate. So now I'm going to renumber these. So now I have 10 oxygen atoms on the reactant side. I also have 10 oxygen atoms on the product side. But I have 4 nitrogen atoms. So I take the coefficient and multiply it by the subscript, and that gives me the number of atoms I have. So 2, my coefficient, times 5, my subscript for oxygen, tells me I have 10 oxygen atoms. That's how those numbers come to be. So am I balanced? Well, my nitrogen, I only have 2 nitrogens on the reactant side. So I need to put a 2 for the coefficient so that I'm multiplying 2 times 2 in order to get 4. And then I have a balanced equation. Now this is called a synthesis reaction. Here we have reactants that are smushing together, reacting to synthesize one product. Now, if we were to read this in a narrative fashion, this would be 2 moles of gaseous nitrogen react with 5 moles of gaseous oxygen in order to form 2 moles of dinitrogen pentoxide. So let's try another. If I have NH4NO3, I'm going to call that a gas. And I'm going to decompose that into nitrogen, oxygen, and water. Now we've added another layer of complexity because we have 2 compounds that have oxygen in them. So we need to be careful about where we're putting our coefficients. So first, let's write down the atoms that we have on the reactant side and the product side. So let's just give it a count. We have 2 nitrogen atoms, 1 here and 1 here. We have 2 nitrogen atoms on the product side. On the reactant side, I have 4 hydrogen atoms, and on the product side, I have 2. On the reactant side, I have 3 oxygen, and on the product side, I have 3 oxygen. So it seems fairly straightforward, except for the hydrogen. Now, because hydrogen is over here with water, if I put a 2 here, not only does that change my hydrogen, but it also changes my oxygen. Now I have 4. So this one's going to take a little more doing. So if I need to change this into an even number. So if I start by putting a 2 here, and then my reactant side, then I have 4, 8, and 6. So now it becomes a little bit more interesting. So if I put a 4 here in order to get 8 hydrogen, then I have 4, 5, 6 oxygen, but I still only have 2 nitrogen. But this is an easy one to solve, because if I put a 2 here, then I have a 4 here. Double check. 2, 4, 8, 6, 4. 4 times 1 is 4 oxygen, plus 2 more is 6. Hydrogen is 8. Now we have a balanced chemical equation. This is also a decomposition reaction because we have one reactant breaking into constituent compounds. We have a decomposition reaction, and these are gases. Remember, nitrogen and oxygen in their elemental form are gases. They're diatomic gases. So let's try another one. If we have something like solid iron reacting with liquid water, and that would be shown with a lowercase l, to form iron 3 oxide, and that's going to be a solid, and gaseous hydrogen, we need to balance this reaction. So we have 3 atoms that we need to pay attention to. We'll count our reactants and our products. So for the iron, we have 1 on the reactant side and 2 on the product side. For our hydrogen, we have 2 on the reactant side and 2 on the product side. For the oxygen, we have 1 on the reactant side and 3 on the product side. Now, because I only have oxygen in one place on either side of the arrow, then because I have 3 on the product side, I'm going to put a 3 as my coefficient on the reactant side. Then that gives me 6 hydrogen and 3 oxygen. The hydrogen is by itself, so I can put a 3 here and make that 6 hydrogen, and the iron is by itself, so I can put a 2 here. So then my balanced reaction becomes 2 iron plus 3 water reacts to form 1 iron 3 oxide plus 3 hydrogen. Now this is called a single displacement or replacement, depending on the textbook that you're looking at. Single displacement or single replacement reaction. If we have titanium chloride, and it's a solid, and it reacts with gaseous water to form titanium oxide, again a solid, and hydrochloric acid, a gas, then what we're showing here is called a double displacement. You may see it as double replacement. Depends on your book. So what you have is you have your cation replacing the other cation. So the titanium is going to come in and knock out the hydrogen. The hydrogen is going to come in and replace the titanium. So we have what's called a double displacement. But first, let's balance it. So we have our titanium, our chlorine, hydrogen, and oxygen. We have our reactants and products. On the reactant side, we have 1 titanium, 4 chlorine, 2 hydrogen, and 1 oxygen. On the product side, I have 1 titanium, 1 chlorine, 1 hydrogen, and 2 oxygen. Now I'm going to start with chlorine for no other reason than it seems fairly straightforward. So I'm going to put a 4 here, and that's going to change the number of hydrogen and the number of chlorine that I have. It balances my chlorine. Now for the hydrogen, I'm going to put a 2 here, and that's going to make 4 hydrogen and 2 oxygen. Now it looks like I have a balanced reaction. So I'm just going to double check. I have 1 titanium on both sides. I have 2 oxygen on both sides. I have 4 chlorine on both sides, and I have 4 hydrogen on both sides. So this double displacement reaction is balanced. Now, when you have a compound, an ionic compound, and it happens to be an aqueous compound, so something like calcium, let me change my pen here, calcium chloride. And that's aqueous, that's in water. So we give it a little AQ to indicate that it is in water. And it reacts with silver nitrate. That's also aqueous. What we're going to form is a double displacement reaction, or at least that's what's possible. When you have an aqueous compound, what you have is a homogeneous mixture of all of the ions that are created from that aqueous compound. So rather than having calcium chloride, what you have is calcium ions and chlorine ions or chloride ions. And what happens when they're in this homogeneous mixture, I'm just going to break them up down here, but I'm going to leave the little AQs off, just to keep things a little bit neater. And so I have my silver cations and I have my nitrate anions. So they're all swimming around in this aqueous soup. Then they have the potential of making 2 new compounds. And those 2 new compounds, it's a double displacement reaction. So if I take my calcium and I trade places with my silver, then I could be making silver chloride, or I could be making calcium nitrate. Let's make our calcium nitrate the correct chemical formula. So what I need to learn is this a precipitation reaction? If it's a precipitation reaction, then one of these products is a solid. So you have a solid falling out of solution. In order to know if it's a precipitation reaction, you need to know how to read what are called solubility rules. And here are our solubility rules, and this is one way to look at them. Your book, your textbook, or your classroom may have a more succinct way, but regardless of how it is presented, they are the same rules. So what I'm looking for I'm going to start with my cations. So I have chlorine or chloride and I have nitrate. So I'm going to read here. I'm looking for nitrate first, and I see nitrate mentioned right here. Now, soluble compounds contain nitrates. So I can be fairly certain that because this contains a nitrate, that this is an aqueous compound. It will not precipitate. So I'm looking for silver chloride. So I'm going to look for chlorine first. Now, soluble compounds contain chloride ions. Okay, well, that means I do not have a precipitate reaction, so I need to read about my exceptions now. 2 of these solubility rules include halides of silver. You have to remember what a halide is. Remember, a halide is a halogen that is an anion. Your halogens are fluorine, chlorine, bromine, iodine. So because chloride is one of the halogens and it is an exception to the solubility rule, that means this is a precipitate. So the silver chloride comes out of solution. Now, because this calcium nitrate is aqueous, and we just said that aqueous compounds swim around in a soup of their ions, so like this, then on the product side, we have these ions as well. So because these ions kind of hang around and watch the precipitate be made, these are called spectator ions. This entire form of a chemical reaction here, or a chemical equation, this is called a complete ionic reaction or equation. If we were going to form the net ionic equation, then what we would do is distill down what is happening, what is forming that is not just aqueous and in solution. And the answer is the non-spectators is what is forming. So what I have is silver, that is aqueous, reacting with chloride, that is aqueous, in order to form my solid silver chloride. So here I have the possibility of a double displacement reaction, but when I do that double displacement reaction, I form a new solid. So this is called a precipitation reaction. Now let's practice predicting the products of a reaction. If we have potassium iodide, and that is aqueous, and that reacts with lead nitrate, which is aqueous, what will we form? Well, this is going to be a double displacement reaction. At least it has that potential. So I'm going to put my potassium with my nitrate, and I'm not going to say what it is yet. I don't know if it's aqueous or if it's solid. So I'm just going to leave the phase off for now. And if I transfer my potassium, and if I use my potassium to combine with my nitrate, then I must be combining my lead with my iodide. Now remember your charges when you're making these chemical formulas. So lead is a +2, and I know that because nitrate is a -1, and there are 2 of them. So lead is a +2, and iodine is a -1. So I must have 2 iodides here. So before I go up to my solubility rules, let's balance this equation real quick. I have 2 nitrates on the reactant side, so I'm going to put a 2 in front of the compound on my product side that has nitrate. So now I have 2 potassiums on the product side, I need 2 potassiums on the reactant side, and that happens to balance my iodines as well. So this is a balanced equation. So now let's use the solubility rules and predict the phase of these compounds. So I'm looking for nitrate and I'm looking for iodine. So here I have soluble compounds contain nitrate. And I have soluble compounds contain the halide ions I. So I need to look at my exceptions. Exceptions to the rules include halides of silver, mercury 1, and lead. That 2 is in the wrong place. So because this is lead 2 halide, that means this is a solid. It is a precipitate. This is an aqueous compound. It comes out of solution. So my spectator ions, the ones who are still stuck in the soup, my spectator ions are potassium as the cation and nitrate as the anion. The net ionic equation is going to be the net of what happens. If I wrote out the complete ionic equation here, and I crossed out, well, now I broke that apart. That doesn't get broken apart because it's a solid. And I cross out the sides. So the potassium, which is my spectator ion, the nitrate, which is my spectator ion, then what I'm left with is the net ionic reaction. Make sure it's balanced, and that is your net ionic reaction.